Hi, everyone. Today, I'm going to talk about the limitations of autoregressive models and their alternatives. In NLP, there are two popular model architectures. The first is autoregressive models. They are widely used in language modeling and many seek-to-seek applications. The second is energy-based models. For example, fine-tuned BERT models. In this talk, we ask the question whether the two are equivalent in expressiveness. One of our main results is no. Energy-based models are strictly more powerful. In this talk, we will also see how model families that are more expressive than autoregressive models must make their own trade-offs for expressiveness. We first briefly review autoregressive models and explain why they are weaker than energy-based models. Many NLP tasks require comparing the goodness of different strings. This is often done using neural networks in practice. When we feed different strings into the network, we will get different scores, and we train the network to approximate our scoring function. We regard the non-negative network output as the goodness function of the input. The network can usually be evaluated in polynomial time in the input sequence length. We also define the support of goodness to be the set of strings whose goodness is greater than 0. We often also want to score the goodness in an absolute sense. This will allow us to compare goodness between different models. Conventionally, we normalize the goodness to a value between 0 and 1. In this case, the goodness function is a probability mass function. To normalize goodness scores, we need to compute the partition function z, which is generally intractable. Fortunately, there's a subclass of energy-based models that allows efficient computation of normalized goodness scores. In other words, they define probability mass functions directly. Such models usually have a softmax layer at the top of the network, and they define conditional probabilities over all types in the vocabulary. For example, to get the score of a string, roses are red, we'll first fit in the string start symbol and get the conditional probability for roses. And then we also fit roses into the network to get the conditional probability of the word R. And then red. Now, we take the product of all conditional probabilities as a goodness score of roses are red. More formally, an autoregressive model takes a prefix as input, and it defines conditional probabilities over all possible continuations. All conditional probabilities can be computed in polynomial time of the prefix length. Since autoregressive models factorize a normalized distribution into a bunch of factors, the partition function is guaranteed to be 1 if the model is consistent. So we do not need to normalize again. We can also sample from an autoregressive model easily, but we cannot do so for energy-based models. As we said at the start of the talk, autoregressive models must give up expressiveness for such convenience. In fact, in this paper, we also identify other model families that are strictly even more powerful than energy-based models in terms of the language classes of the supports. Now we want to share an intuition why energy-based models are strictly more powerful. Suppose we want to model from a language where strings are of the form formula followed by assignment, where formula is a Boolean expression and assignment is a Boolean vector. We require that the goodness function must be greater than 0 if the assignment satisfies the formula, and 0 otherwise. We can show that such a goodness function can be implemented as a neural network. On the other hand, can we implement that goodness function using an autoregressive model? Computing the first token right after the encoding is hard, because in general, we need to consider all possible continuations, even just to decide the first token. For example, the probability of A1 equals 0 given the formula has to be small or 0 if there are few or no satisfying assignments that have A1 equals 0. And there are exponentially many possible continuations. Apparently, converting the huge branching tree to an autoregressive model takes a lot of computation, and we cannot store the pre-computed results in a fixed size model. In contrast, energy-based models do not need to check all continuations. They just need to ensure that they can score a single one. In other words, energy-based models do not need to know how to compute the partition function. More formally, we can show that computing the conditional probability of the first bit is an NP-hard problem. Therefore, no polynomial time autoregressive model can model such conditional distributions if P is not equal to NP. Actually, we can show some more stronger results. There are distributions that can be captured by energy-based models, but no autoregressive model can capture the distribution exactly, approximate them well enough to get the same ranking of strings, or even just to approximate within any multiplicative factor. The common question here will be, why should we care if our datasets are all finite? In other words, we should be able to make the model larger if a smaller one doesn't work because of the lack of capacity, right? It turns out that realistically speaking, we cannot just make a larger model when a smaller one doesn't work. If the model size only grows polynomially in the sequence length and takes polynomial time to compute the probabilities, they will belong in the P/poly class. In other words, given the assumption that NP is not a subset of P/poly, the models will have to grow super polynomially larger or run super polynomially longer in sequence length to model the formula assignment problems well. Now, you may also ask, why should I care if I am not interested in solving set problems? It turns out autoregressive models in general cannot capture distributions over strings of the form problem followed by solution, where the problem is computationally hard to solve. Many computational linguistic problems are computationally hard. For example, parsing of many formalisms, propositional logic, which is crucial for general logic inference capabilities, optimality theory, etc. Therefore, important linguistic regularities cannot be captured by autoregressive models. We wanted to use propositional logic as an example to show how autoregressive models cannot capture certain distributions. But that would be a bit boring, so instead we talk about Star Wars. Let's assume that we have a really, really powerful autoregressive language model called GPT-3PO. GPT-3PO is a really good storyteller. Today it's gonna tell us a story from a galaxy far, far away. So a long, long time ago, in a galaxy far, far away, the rebels fought against the Galactic Empire and eventually won. The story started with Luke. Assuming that the story GPT-3PO tells us is a Star Wars story, there will be a point where Vidar, who is the bad guy here in the movie, say to Luke, a rebel hero, that, look, I'm your... Now, GPT-3PO has to continue the conversation. Could it be friend after these first three words? Since I'm your friend appears to be a frequent foreground, the word choice seems to be very plausible. So Vidar and Luke will continue to be good friends and enjoy their friendship. And since Vidar is the bad guy here, and who wanted Luke to also be a bad guy, he will turn Luke to the dark side. And that somehow goes against what we assumed at the beginning, that the rebels will have won. So here's another word choice, father. Father is indeed the observed answer. We note that it was decided that Vidar was Luke's father even before the movie production. In other words, humans use look ahead to decide that the word should be father here. And now we get to an ending where the rebels won following this line. The continuation, I'm your friend, sometimes doesn't result in an ending we wanted because of inconsistency with earlier parts of the story. We want to know if we can tell such a story as soon as possible. In other words, we wonder if we can learn the conditional probability of friend should be low. It turns out that we can't. Moreover, under smooth distributions that assign probability mass to every string, no autoregressive model can assert that an inconsistent continuation will have lower probability than a consistent continuation, even when both continuations are of similar lengths. A brief summary so far, we see that autoregressive models cannot even guarantee that the generated continuation is consistent under propositional logic. This is bad because checking such an inconsistency should be easy. Speaking very loosely, autoregressive models cannot tell between a surprising plot twist and an inconsistent continuation. Now, we look at alternative model families that are more expressive than autoregressive models. We have discussed autoregressive models. They have fixed model size, and they support both efficient scoring and sampling of strings, but they assume a left-to-right factorization. It turns out that if a distribution has a certain supports in P, in the class P, then the factors will be NP hard to compute. So autoregressive models cannot deal with such distributions. At the beginning of the talk, we already introduced energy-based models. Since these models do not factorize, they don't need to worry about the NP-hard factor computations of autoregressive models. But also because they don't factorize, it is hard to sample from such models. Now, we will consider another model family, autoregressive models, where we also allow latent variables. In our previous example, we said that autoregressive models may not prefer plot twists like, look, I'm your father, to other more bland but logically inconsistent continuations. But actually, autoregressive models are capable of generating such plot twists. It just needs some more backstory to help it justify the climax building. In other words, we will need a backstory such that the plot twists feel like a natural continuation. And there happens to be one for Star Wars. In our galaxy, the story started with Luke, and we only came to know that there was a backstory some 20 years later. But suppose GPT-3PO tells us the backstory first, namely, the story that in a galaxy far, far away, Vidar became Vidar, and also Luke's father. Under this story, we don't need to look ahead to see why the plot twist makes sense. In fact, we can look behind to prove that Vidar was not lying. Here, we are only interested in the last story. So the previous three stories are regarded as latent variables. It turns out that with the right latent variables, even autoregressive models can do propositional logic. In fact, they can model any NP language. The thing that autoregressive models have to give up is efficient scoring. Since there are latent variables, they must be marginalized out, and that can be expensive. Now, we'll look at another model family, lookup models. We showed that for some language models, it takes a lot of computation at runtime to predict the next word. An alternative is to pre-compute these results at training time. Then, at runtime, we just have to look them up. If the model size is not bounded below some function of the sequence length, then, of course, you can memorize anything you need and model any finite language you want. In most machine learning applications, the ability to model finite languages is enough. The memorized stuff is generally indexed and stored in a way such that retrieval takes time sublinear in database size. Examples of lookup models include KNLM and adaptive semi-parametric language models. However, lookup models give up model compactness, so the parameter factor can use a lot of space. Moreover, if the factoids are stored in a database, then there's no obvious way to learn such a database from annotated data. In this work, we show that autoregressive models are inherently limited. We show that unless they use superpolynomially many parameters or superpolynomially long runtime, they cannot deal with certain easy distributions that non-autoregressive models can. We also induce 3 alternative model families that have strictly more expressive power than autoregressive models, but each of them comes with their own trade-off. Please check out our paper. Thank you.